Hello and good morning, and hopefully those of you that came and saw us on Monday night enjoyed the reception we had, and hopefully it's something we'll do every year. It's the second year of doing that. And what I'm going to do today is to talk about custom instructions and the sort of the challenge, the puzzle of them when it comes to the ecosystem and the technology and the products, the conundrum of it. I'm going to talk a little bit about why people are looking at RISC-V, and obviously we've heard a lot about that over the last day or so, and really talk about the freedom and the cost of that freedom, and then talk about custom instructions and the challenges that poses to the teams designing, verifying, programming, and everything, and address how we're addressing that. So why are people trying to adopt RISC-V? If we can boil it down to several different things, but the way I look at it, I think the world's changed in terms of the existing ISAs. Yes, clearly MIPS has moved away, now it's doing RISC-V. ARM is changing its business in several different ways, and that's sort of commercial side of things, but there's actually a product side of things, a technology side of things. An end user has demands on technology now, and a lot of it's software driven. Most high-end technology, it's all software. Everything we interact with really is software there. That means electronic products have to change, and we have to change the way that we build them and test them. And the third thing really is that it takes an awful lot of effort to build all this technology and do things. So we need to be more collaborative because of the cost, the timescales, and the complexity. So those things are suggesting we need something better. So it's really a sort of perfect storm coming together of different needs and opportunities intersecting. We need to do something differently, and RISC-V is in that space. And why is it so attractive is several things. One, it's an open standard. It is free and open, and we can access it easily. It's evolving quickly. We just saw Mark saying this year there's 12 extensions going to be ratified. Next year there's already in progress identified 14. So it's evolving and changing. But what that means is people are going to be able to configure things to be smaller or larger, and they can focus and scale it based on the problem they're trying to solve, the process that they're trying to create. And we're going to see a lot of domain-specific processes, and that's really what is attractive in RISC-V. It enables this freedom, and that's very important. It's the freedom, we think, that it enables. But there's costs to these freedoms always. If you're building your own technology, you've got to do much more analysis on it. You've got to get software running early to see whether the architecture you're building, this domain-specific process, it does what you need. Because these software-defined electronic products, you have to verify that the software is going to run on it before you commit to however long the RTL takes and the costs of that. And there's technology simulation called virtual platforms are very much needed to use that, to get the software running. And we've had people using virtual platforms a year before the RTL's even fixed, or even they've chosen the IP related to it. So it's very important with software-defined products to do simulation and stuff early. The second thing is you need much better verification technologies in there. And I talked last year, actually, I don't think it was on this stage, but at the summit, about the challenges that people have in verification. And I quoted some data from ARM where they do 10 to the 15 cycles of verification on a high-end processor. And on the state-of-the-art system Verilog simulators, that's 15,000 years. If you go through the numbers, or 30 years on an accelerated FPGA. And that sounds a lot, but actually, if somebody's doing, a big chip, doing 2 years on the verification with a lot of hardware assist in there is actually what it's taking. So it's very important to do a lot of verification to get the quality up. But then what custom instructions do is they add a lot more complexity to that. So you have to have much more sophisticated modeling and much more sophisticated tooling to really get to the quality levels you need if you're going to make use of the freedoms that RISC-V is providing for you. Now, I'm going to talk about two different things, the modeling and the verification, and talk about how that sort of starts off and how we get into the custom instruction side of things. And the sort of basic requirements that you need on a model, it's got to cover the specification of the standard, but it has to evolve with it. I mean, I don't know how many actually extensions there are. There must be over 50, 60 now in the specification that have been ratified, and whether they're small bits or large bits. But the model has to be able to be configured to be able to represent those accurately, and it needs to be accurate. It needs to be fully verified, ideally used by a lot of different people, and you really want something that is evolving and maintained, and you can talk to about how it's running and maybe how it's different from what you're expecting in there. You need a model that's controllable, so you can set it up the way you need it. It needs to be analyzable, so you can see how the software is actually running on it. So you, especially if you're building your own extensions in there, because one of the things you've got to do is have a model which is the base, but also that is extendable in there. And one of the things you've got, if you've got a model that's running, it's no good running it in isolation. You're going to run it with the other uncore components. You want to simulate that. You want to boot Linux, you've got to have all these other technologies in there around the processor. So you need a model that actually works in industry solutions, like the technologies that provided by Cadence or Synopsys or Siemens Mentor, from an industrial sort of RTL simulation point of view. You want to simulate the whole system in there. And also, a very important thing is, as software is defining these products, you're getting more and more compute in there, whether I'm not going to use the word AI, I was going to say I'm probably the only presentation that does, but if you're doing modern workloads in there, you're going to need a lot of speed in terms of the simulation to just run it. Booting Linux, on RTL takes 40, 50 hours, so you need high performance technologies. And it's very hard to achieve that. All these different things pushing the model in different directions that are requirements. Now, from an Imperas point of view, we're a commercial company, and thanks to the customers, they pay us for our technology so we can come to conferences, we can sponsor parties like on Monday night. I mean, we've been building technology around models for 15 years now, around some open standard APIs that we helped create, and we've done all the traditional ISAs. I think we support 17 ISAs at the moment with our technology, but originating with some of the ones like MIPS and PowerPC, ARM, ARC, and stuff like that. And in 2016, started talking to Krista about RISC-V. We started getting involved in that, developed commercial models in there. People are using them for architectural exploration, they're using them for software development, and they're using them for verification in there. And we have a lot of different models. We work with a lot of different people. These are some of the models available publicly, and I don't expect you to see them all. You can go and look at our websites and see what there is for the different IP providers that we work with. And top right, the sort of IP providers on the left there, really. And top right, we support all of the different bits of the RISC-V standard, and actually in some cases we've been the first simulation of some of the earlier unyet ratified standards. And not only do we have this sort of public simulation, we also have models of proprietary extensions that people are working on as well. So we have a lot of different modeling technology in there. And yeah, I said it's very hard to achieve this, but we think that our fast processor models really have it covered in there. So if you need models, we have a very good answer for that. And when you've got the base model, we can configure it and customize it for the way that maybe your IP vendor needs it. Then you can extend it and configure it and add your own technologies to it. And almost everybody we deal with is building their own extensions in some form of custom instructions in there. So our technology allows you to do that. And we provide some technology open and free on GitHub and on our websites, which has tests and simulation. That's a list of some of the companies in February that are downloaded pictorial list of our technologies in commercial companies, universities. A lot of people are using it all around the world with this technology because we really are embracing what's going on in the RISC-V world. And pretty much we work with most people. Bottom right, we've got tool partners, whether it's Brecker in the system integration, Valtrix in the test generation, Cadence, Synopsys in the system sort of simulation side of things. We work with the processor IP vendors, so we have pretty much everybody's models. And then we have commercial companies doing their own thing with our technology. So most processor people are using Imperas in some way there. And when it comes to custom instructions, yes, we have our basic model that is delivered, which has the base RISC-V stuff in it. It has whatever the IP vendor might have in it. But our technology and methodology allows you to add custom instructions, custom interrupts, custom state in there, and communication. So you can change the model. When we have technology simulated, obviously, we have technology to analyze it in terms of profiling. So you can actually see the performance of these new instructions, how it changes things, how the software runs and everything. And so for custom instructions, you can take what we provide or our IP providers or partners provide, and then it can be extended and you can iterate to find out what the architecture you really need, whether it's single core or you can put multiple cores together in there. So we have technology and methodology to help with extending it with custom instructions and state. And when you've got that model and you've got it working, You can run it in verification. I'm going to give an example of that in a minute. And we have virtual platform technology, so you can actually simulate your whole system, SMP, Linux booting. Our models can also be used with our partners in Cadence in their Helium technology and Synopsys in their virtualizer technology. And so the model can be used. And in verification, what I'm going to do is just give you a quick example of this. This is a core that we're working from, an academic university core here in the US, which is actually the focus of a book that's coming out on processor and architecture design. And prior to working with us, they've got the RTL going, they've got compatibility tests running, they had simulating in RTL, and they got up to like 90-odd% code coverage, which is actually pretty good. And they were using a methodology where sort of signature compare, where they would write out on the RTL some values and write out from the simulator. And they had Linux booting, which is pretty good. Runs in Verilog, runs in FPGA, so that's a good place to be. But is it finished? Is it done? Is it verified? And one of the things we're doing to address that is we're building system Verilog functional coverage. Now, there's 1,000-odd instructions in RISC-V. Each one's going to need 40 or 50 lines of Verilog to do coverage analysis on it. So we've automated the whole thing, which is up to about 200,000 lines of Verilog that comes with our technology now. And it actually works in the DV side of things. So it's actually looking for functional coverage on hazards. It's telling you whether your tests have stimulated that. And it works off a standard interface from the RTL. And it measures how much verification has been done. And we have a technology, our Imperas DV product, which takes the model, takes the coverage, hooks up to the RTL. You run your programs on the RTL, and on every event, it's comparing. So it's actually doing checking of that. And it checks the mismatches and tells you if there's anything it doesn't understand. And it does all the asynchronous stuff. And after using our technology, they found 20, 30 different bugs in there to do with different, very complex things. And actually, recently, we just provided some tests for virtual memory, and it's finding more bugs in that. So with verification, it's very important that you find a good methodology that works. And things like post-simulation trace compare and signature compare, they're sort of good enough for some things, but they're not a commercial level. You need something a lot better. Running applications like Linux is great. It shows you've got something, but it's not verification. So from a verification point of view, you really have to have very high quality and accurate and controllable model, but also some very innovative technology to do the verification on something as complex. But the challenge is, it still takes a long time. Booting Linux on that CVW core takes 40 hours on a Verilog simulator. So we started working with the big EDA companies with their hardware assist to try and improve this verification, because we think we can probably get what was 40 hours down to about 5 minutes. So that means if you find bugs, you can turn around much more quickly. So we're working on that, and that's something for the future there. So just to wrap up here, this freedom that we have with RISC-V is phenomenal. It's changing everything, but it's not free. People want it because of the freedom, but there's costs to that. And the costs are that you've got to have better technology to help you design it, ensure it's going to work, that it's verified. And one of the challenges with verification is it's sort of an endless problem. There's the verification costs of finding the bugs, to actually find them, but actually there's the impact cost of the bug escapes, because if you haven't found the bugs. So there's a lot of challenges still to come. There's obviously, Mark's talking a lot about the software side of things. We tend to focus on the architecture and the verification and the modeling of it. And when you add custom instructions, you're really adding much more complexity to the challenge that you've got. And that's work that we've all got to keep working on to move that forward. And you've got to make sure you make good choices on the tools and the models and the methodologies. And if you want to find more about it, we're down on the show floor. Come and talk to us later today. Thank you very much.